polynomial solutions of a discrete analytic function. So how do you do this? You do the Ehrenpreis trick, and you try to find solutions of this equation, in other words, to find discrete analytic functions of this form, the same old trick with discrete analog. You plug it in, and then you get z to the power wn plus I times z to the power n plus 1 wn minus I times z to the power m w to the power n plus 1 minus z to the power n plus 1 times w to the power n plus 1. You take out z to the power w, plug the power n, and you have the condition 1. This is called the symbol of the operator. Minus dw equals 0. Now you solve for w, so you know you have many, many solutions. 1 plus I z over z plus I. So you have z to the power w times 1 plus I z for any complex number. But, and any linear combination of this is also discrete analytic function. And any integral over the complex plane, the continuous complex plane, unfortunately, is also a discrete analytic function. But the ideas of Ehrenpreis enabled me to give a one-line proof to the discrete Liouville theorem. Reminding you from complex analysis, Liouville theorem says entire complex analytic function of bounded growth is always a constant. And this is a more general version. If it's polynomial growth, it has to be a polynomial. But now, if you look, if z equals 1, then you get 1 and 1. If z equals minus 1, you get minus 1 and minus 1. But using the idea of multiplicity varieties, you can construct polynomial solutions to this discrete Cauchy-Riemann equation. In other words, get a natural basis to discrete analytic polynomials. Unlike their continuous counterparts, discrete analytic functions are not closed under multiplication. So it's very easy to multiply two analytic functions, you get another analytic function. So the basis is naturally z to the power n. Z is, of course, complex analytic, so z squared, the cube, but things are not so simple. You cannot just multiply, take the simplest one, which is m minus in maybe, I'm not sure, and take a part. But take this kernel, z to the power m. If z equals 1, you don't get something very interesting. You get a constant function, 1. Yeah, 1 plus I over 1 plus I. So when z equals 1, you get 1. It's not very interesting. Of course, 1 is decision. 1 is discrete analytic exercise for you. 1 minus 1 is 0, 1 minus 1 is 0, 0 over 1 plus I, 0, and so on. But now is the Ehrenpreis trick that got me a whole paper. Take the derivative with respect to z. Any number, and then plug z equals 1. And then you get the Zeilberger basis for discrete analytic function inspired by Ehrenpreis. And 35 years ago, I did not have maple, but now I do. So I programmed this and generated a basis for the first 100 polynomials. And by the way, it's a maple package I wrote in memory of Leon, called Leon. If you know how to use maple, you're welcome to download. I'm going to post it in a few days. download Leon from my homepage, and you can get it. So in about 10 seconds, or maybe 20 seconds, it can generate the first 100, all the polynomials of degree less than 100 to the discrete analytic function. And if you do it by brute force, it's not so hard. It's possible in principle. You write undetermined coefficients, you plug it into the equation, you have a huge polynomial with undetermined coefficients, you expand it, maybe I can do this, you set every monomaly with a 0, you have a huge system with 1,000 equations and 1,000 unknowns, and if you go up to degree 1,000 with 100,000 equations and 100,000 unknowns, and Maple in principle, and you can cheat and use MATLAB, MATLAB is not that reliable, give you the solution. But with the Ehrenpreis idea, you can do it 100 times faster. Because to take a derivative with respect to z, and plug it then z equals 1, it's much, much faster than solving this huge system of linear equations. So even conceptual mathematics a la Leon can also be very, very important computationally. And Leon, I think, did not see a contradiction between all the, what people think is contradictory. Science and religion was not a contradiction. Everything could be settled. Conceptual and computational, theoretical and experimental could all be resolved at the end. So let me finish with another quotation for the beginning of this beautiful commentary of Leon that I hope the family will allow me to post. I asked permission, but they're still thinking about it, because it's really a masterpiece. So this is, his Hebrew name was Eliezer. So this is Kitvei the Rabbi Eliezer, the writings of Rabbi Eliezer. Chelek Aleph, Part 1, Bereshit, Genesis, by Rabbi Dr. Eliezer Ehrenpreis. So he was stressing that he was a rabbi and a mathematical PhD. He was not bragging, he was just trying to tell you the synthesis between the two. And then he tries to define truth. And then he had a quotation from Tehillim, Psalms. This is the motto of his masterpiece commentary. That I hope will be published at least on the internet. And I was told by his wife that he finished the whole first books of Moses. I only have Genesis, the first book. So I very much hope that they also send me the other stuff. So it says, Mishpatei Adonai Emet. I tell you in a second, wait. Tzadku Yachdav. The statements or the sayings of God is true. They are true together. And this is his definition of truth. There's only one truth. And the truth has to be consistent. And if you have a consistent worldview, if it fits together, then it is the truth. And Leon believed that he reconciled the Torah and so-called modern science. And he has beautiful, that some people may consider crazy, explanations why the world was indeed created only 5,771 years ago. And the constants, for example, entropy could have changed, and the Heisenberg identity principle featuring Planck's constant could have changed, the speed of light could have changed, and this, he was also quoting his great hero, Dirac, that also had this idea that constant could change. So for Leon, everything was consistent, there was no contradiction, and he was really the epitome of truth. Thank you.